Hello and welcome to section 2.7 on rates of change in the natural and social sciences. This section of the textbook covers a few types of examples from a variety of fields. The following examples are presented so that you will acquire the ability to recognize rates of change, and thus derivatives, arising in the sciences. What is the current of a stream? How do we characterize this in a way which we can quantify? Flow is the total volume of a fluid that flows past a fixed point in a stream over time. The speed with which water moves along a stream is related to flow. Suppose a bridge crosses the stream. The function w will represent the flow of the stream passing below the bridge on the time interval 0 to t. The current of the stream is the rate at which the flow changes with respect to time t. That is, the change in volume with respect to change in time. We can discuss the average current just as we do average rate of change, and we can discuss the instantaneous current as the limit of the average current. To summarize, the derivative of flow is current, just as the derivative of position is velocity. Similarly, given a charged wire with an excess of electrons on the left and a deficit of electrons on the right, we can measure the amount of charge that has passed a sensor from time 0 to time t. Q of t is the flow of charge, just as W of t was the flow of the water. As with flow, the current along the charged wire is the rate of change in the charge Q with respect to time. And as before, we have the average current for the average rate of change and the instantaneous current for the limit of the average current. Let's return to the example of flowing water. As you've probably noticed in real life, the current of a stream is not uniform. There are many factors determining the current at a point, but typically the current is fastest near the middle of the stream. Friction and turbulence slow the water down near the shore and the stream bed. Let's simplify our setting from a stream to liquid flowing through a smooth cylindrical tube. The liquid will flow from high to low pressure, and the axis of the tube is the line passing through the center of the cylinder. Liquid near the walls of this tube will move slower than liquid near the axis. This is described by the law of laminar flow. Let P represent the pressure difference between the left and the right end of the tube. Let eta represent the viscosity of the liquid. Let L represent the length of the tube. And let R represent the radius of the tube. The law of laminar flow gives the velocity of a liquid a certain distance, little r, from the axis. Question: how fast is the velocity of the liquid decreasing as we move from the axis to the wall? That is, what is the trend in velocity from v1 to v2 to v3 to v4? What we are looking for is the change in velocity v with respect to the change in radius from the axis, little r. dv over dr is called the velocity gradient. We can calculate the velocity gradient by taking the derivative with respect to little r of v. Notice that the equation only possesses two variables, the velocity v, which depends upon the radius from the axis, little r. We will assume that the tube is fixed, hence L and big R are constants. The liquid has been chosen, hence eta is a constant, and the pressure on each end is constant, hence P is constant. Therefore, we can take the derivative with respect to little r. Notice that the left part of our expression is constant, hence has a derivative that is 0. Recall that our variable is little r, the distance a point is from the axis, and the velocity gradient measures the change in speed as we move a point away from that axis. Also notice that the actual radius big R plays no part in the velocity gradient. As the point moves farther away from the axis, little r increases, and the velocity gradient becomes more negative. That is, as you get closer to the wall, the speed of the liquid decreases. The slowdown is twice as fast in a tube with twice the pressure as P is in the numerator. The slowdown is half as fast in a tube which is twice as long as L is in the denominator. And the slowdown is half as fast in a liquid which is twice as viscous as eta is in the denominator. The equation allows us to see how different parameters affect the velocity gradient. Rates of change are not restricted to the natural sciences. For example, in economics, the concept of marginal cost is a rate of change. Suppose a company produces widgets. What will happen to production costs as the number of widgets produced changes? Well, let C of x be the cost of producing x widgets. Typically, the function C is the fixed costs plus the variable costs in producing a widget. Fixed costs are independent of the number of widgets produced, such as administrative salaries and storage and factory rentals, while variable costs are dependent upon the x, the number of widgets produced. The marginal cost is the rate of change associated with the cost function c. We have an average marginal cost, but does it make sense to discuss instantaneous marginal costs? Delta x is the change in the number of units sold, so you would always expect it to be a whole number. In fact, the function c should only make sense on whole numbers. How would you make a negative number of widgets or a tenth of a widget? Even though c has domain errors, in practice the cost function is a polynomial, hence the derivative exists. In summary, wherever we find an equation of variables, we can find rates of change for those variables. In the natural sciences, we have velocity as the derivative of position, and current as the derivative of flow and charge. Also, in the social sciences, like economics, we have marginal cost as the derivative of cost. The takeaway for section 2.7 is the importance of rates of change and derivatives beyond abstract mathematics.